Alright, today we're going to talk about fire streams. My name is James Parham. I'm captain with the DeSoto Fire Department. So let's get this thing going. Our unit objectives today are going to be to identify the term fire stream and the four purposes of a fire stream, identify the advantages of using water as an extinguishing agent, identify the three types of fire streams and the difference between a straight stream and a solid stream, define the following terms: GPM, PSI, friction loss, water hammer, and nozzle reaction. Demonstrate how to open and close and identify methods of preventing damage to a nozzle and associated equipment. Demonstrate proper methods of handling fire streams. Identify the characteristics of various nozzles. Describe the principle of foam generation and define common causes for the poor generation of foam, and identify the procedures of correcting each. Identifying the advantages, characteristics, and precautions for use of the various types of foam, and assemble a foam fire stream arrangement given the appropriate equipment. The advantages of water as an extinguishing agent: readily available and it's relatively inexpensive, has a greater heat absorbing capacity than most other common extinguishing agents. Water changing to steam requires a large amount of heat and can be applied in a variety of ways. The disadvantage of water as an extinguishing agent: has considerable surface tension, reacts with certain materials, freezes at normal winter temperatures, has a low viscosity or resistance, conducts electricity, and steam generated from the fire stream that can cause serious burns to personnel. The primary principle of extinguishment is by cooling the fuel below ignition temperature. Can also smother by diluting or excluding the oxygen. Vaporization, a process that changes a liquid into a gas state, and the rate of vaporization depends on the substance involved, heat and pressure. Heat absorption involves the heat required to raise a substance temperature and the additional heat to change its state. The specific heat and the amount of energy required to raise the temperature of a specific mass of a substance by 1 degree. In the U.S., we express this as a British thermal unit, requires to raise the temperature of 1 pound of water 1 degrees Fahrenheit. In the standard international system, units ST are in joules kilograms per Kelvin, but we'll stick with the U.S. version. Energy is also needed to change a liquid into a gas phase. Latent heat of vaporization, quantity of heat absorbed by a substance at the point of which it changes from a liquid to a gas without a temperature change. When water is heated to a boiling point of 212 degrees Fahrenheit, additional energy is needed to change it into a gas, but the water's temperature remains at 212. When water from a fire stream is broken into small droplets, such as from a fog nozzle, it absorbs heat and converts to steam more quickly and in a compact form, such as a form from a solid bore nozzle. How much heat a fire stream absorbs is dependent on the surface area of water put into an area. Obviously, the more surface area exposed to heat, the more heat absorbed. fire stream can be ineffective unless it reaches the fire with enough water to absorb the heat being produced. In some situations, a fog stream might evaporate before reaching the burning fuel, and a solid stream is needed to reach the seat of the fire. Effective extinguishment generally requires steam production. Water converted to steam absorbs more heat than water heated at its boiling point. Water converted into steam occupies several hundred times its original volume to aid in extinguishment. At 212 degrees Fahrenheit, water expands about 1,700 times. 1 cubic foot of water, 7.48 gallons, will occupy a space of 1,700 cubic feet when converted into steam. At 500 degrees Fahrenheit, water expands 2,400 to 1, and at 1,000 degrees expands to 4,200 to 1. The volume of steam produced is also dependent on the amount of water applied. When steam is produced by contacting surfaces hotter than 212, water is vaporized, which adds to the upper layer of smoke and hot gases. The upper layer then expands downward, creating dangerous conditions for firefighters. When water turns to steam in the upper heated layers, this layer tends to shrink. The energy needed to vaporize water is greater than required to cool hot gases. The hot gas temperature drops faster, decreasing the volume of hot gas. A good nozzle control coordinated with ventilation provides effective and safe fire stream operations. Pressure loss and gain. To be effective, enough water must exit a nozzle at adequate pressure to reach a fire. Pressure, the application of force, pounds per square inch, PSI, and gallons per minute, GPM. Friction loss. A part of the total pressure that is used to overcome friction while forcing water through pipes, fittings, fire hose, and adapters. As water flows through hose, couplings, and appliances, water molecules rub against the side of the item and friction is produced. Most common friction loss occurs in the hose between the pumper and the nozzle. If the speed of the water traveling through a hose line is increased above its practical limit, the friction loss becomes so great that the water is agitated by the resistance. In general, the smaller the hose diameter and longer the hose lay, the higher the friction loss. Factors which affect the amount of friction loss: the amount of water moving through a hose, size of hose, length of the hose layout, number of bends and kinks in the hose, obstructions in water streams, rough lining in the hose, more adapters than necessary, and damaging couplings. Elevation loss and gain. Elevation refers to the position of the nozzle above or below the pump. The pressure loss occurs when the nozzle is above the pump. Pressure gain occurs when the nozzle is below the pump. Water hammer. The sudden surge of pressure in a water system, hose, pipe, fire pump, resulting from the sudden stoppage of water flow through the system, such as the abrupt closing of a nozzle or valve. So when we do our practicals, you'll be taught to shut them down, open and close them slowly. To prevent water hammer, all valves including nozzles, hydrants, and hose clamps must be opened and closed slowly. A brief application of water fog at about 150 gallons per minute for about 1 second will not cause water hammer. Nozzle reaction. The back pressure kickback felt while water is being discharged from a nozzle. Factors affecting the amount of nozzle reaction: nozzle pressure, the amount of water being discharged, gallons per minute, and the fire stream pattern. Fire stream. What is a fire stream? A stream of water or other extinguishing agent after it leaves the fire hose and nozzle until it reaches the desired point. That is the stream from the end of your nozzle to whatever you are aiming at, or the fire is considered the fire stream. What is the purpose? To apply water or foam stream directly to the burning material to reduce its temperature, reduce high atmospheric temperature, absorb and disperse hot smoke and gases from a heated area in a confined space, create a barrier between a fuel and a fire. Reduces the temperature over an open fire and thus permits a close proximity with hand hose lines to effective extinguishment. Protects firefighters and property from heat through the use of fire streams as a water curtain, and disperses smoke and gases from a heated area, such as you can use it for hydraulic ventilation. Fire streams are affected by the velocity of the water, gravity, wind direction and speed, air friction, operating temperature. A nozzle design determines the shape of the stream. Nozzle adjustment determines the amount of water flowing. Nozzle adjustment determines the amount of water flowing, and nozzle opening conditions influences the stream's reach. Fire stream sizes: low volume, less than 40 gallons per minute, typically supplied by a 1-inch line, which is commonly your forestry line or booster line. Your handline streams are 40 to 350 gallons per minute, typically supplied by 1.5 to 3-inch line. Master streams are greater than 350 gallons per minute, typically supplied by 2.5 or 3-inch hose line, or they can be supplied by a large diameter hose such as a 4 or 5. The amount of water discharged is determined by the nozzle design and the water pressure of the nozzle. The types of fire streams: effective streams must meet or exceed the critical flow rate, which is the minimum rate where extinguishment is achieved. All fire streams must have a pressure device, the fire pump, a hose, an extinguishing agent, and a nozzle. A solid stream, such as from a smoothbore nozzle, a stream of water shaped by a fixed orifice previous to discharge. They can reach areas other streams may not be able to reach. Get greater reach and penetration into a fire building. Can be affected by gravity, friction of the air, and wind. Characteristics: good reach and penetration, produces a low nozzle pressure, usually half what it takes to operate a combination or a fog nozzle. Produces less steam conversion, produces less heat absorption per gallon, more likely to conduct electricity. A stream that is solid enough to keep its shape even in a breeze. May be easier to maneuver because of lower temperatures, less prone to clogging with debris. It can be used to supply compressed air foam systems. Only one stream pattern available, so you cannot adjust these. Hose lines may be more easily kinked. Solid stream performance depends on the stream's velocity from pump pressure and the orifice size, nozzle pressure, velocity pressure at which water is discharged from a nozzle. A nozzle pressure of 50 psi with smoothbore nozzle produces good reach and volume. A pressure of 65 psi will create reach and volume. More personnel will be needed at pressures over 65 psi. Fog streams are compromised of fine water droplets to expose the maximum water surface for heat absorption. Fog stream nozzles can be adjusted to produce various stream patterns. Fog stream characteristics. Discharge pattern can be adjusted. Amount of water can be adjusted. Can aid in ventilation. Helps dissipate heat through amount of exposed surface area for heat absorption. Does not have the reach or penetration power of a solid stream. Can be broken up by the wind. Can disturb thermal layering and cause steam burns. And can push air into the fire area and contribute to fire spread. Fog streams can range from narrow to wide angle. Narrow has the highest forward velocity. Wide has a shorter reach. Most fog stream nozzles are designed to operate at nozzle pressures of 100 psi at the base of the nozzle. So there's a big difference between the fog nozzles and the solid bore nozzles. Is that a solid bore only requires 50 psi, and the combination or fog nozzle requires 100 psi at the tip to get the full effective use of the nozzle. Straight streams are semi-solid streams produced by fog nozzles. Broken streams are broken into coarsely divided droplets, such as the water curtain or your cellar or attic nozzles, piercing nozzles. This is considered a broken stream. Designed to cover the most space possible with high heat absorption. Coarse drops absorb more heat than a solid stream at greater reach and penetration than a fog stream. Can be effective with confined space fires such as attics, basements, wall spaces, and underground vaults. May have enough continuity to conduct electricity, and it may not reach some fires. Factors which influence the reach of the fog stream or limit the reach of the fog stream. Gravity limits the vertical and horizontal distance of fire streams and cause solid streams to lose their shape. Effective velocity of fire streams range from 60 to 100 feet per second. Solid streams have greater reach than straight fog or broken streams. Air friction affects the finely divided droplets in fog streams. Wind direction and speed can shorten stream reach and deteriorate stream pattern. In ideal conditions, the greatest horizontal reach for a fire stream is at 45 degrees from the horizontal plane. In actual operation, 30 degrees to 34 degrees give the maximum effective horizontal reach. Smoothbore nozzles designed so that the shape of the water in the nozzle is gradually reduced until it reaches a point near the orifice. At this point, the nozzle is a smooth cylinder with a length 1 to 1.5 times its inside diameter. And you can change these tips, and they vary depending on your department's application. The characteristics: operate at low nozzle pressure, normally 50 psi, less prone to clogging with debris. You don't have anything in there. You can look down in there, see the ball valve, so there's nothing to obstruct if you get something in your line. Can be used with the compressed air foam. Hose lines might kink due to less pressure, because if you're running an 1 3/4 pre-connect and you're running a 1 1/8 inch tip or a 15/16 inch tip, you really don't have the reaction force back to or back pressure to keep that line from kinking as you do in your combination or your fog nozzles. So if you're using a line that has a solid bore, a tip on it, especially the guys that are outside, if you see a kink, pick it up. Don't walk over it, straighten it out, because you're helping the guys inside get their job done a lot easier. It's one of my pet peeves on the fire grounds when guys walk over kinks and lines and there's guys actually inside still fighting the fire. It does not allow for different patterns. There's no adjustment. That's all you got. Open and close is the only adjustment you can make on these nozzles. And then we're going to get into some handline nozzle sizes and flows. At 50 psi nozzle pressure. So a 3/4 inch tip, you're going to get 120 gallons per minute. A 7/8, 161 inch is 209. A 1 1/8 is 250 gallons a minute, and a 1 1/4 inch tip, you're going to get 330 gallons per minute, and that's normally out of a 2.5. The 2.5 being supplying that line. Solid stream nozzles for master stream devices. These operate at 80 psi at the nozzle. Usually supplied with a 2.5, 3 inch or can be larger. You can see the different size tips there, starting at the 1 1/4, 413 gallons, all the way up to a 2 inch tip, all the way up to 1,063 gallons per minute. So with a solid bore, you can move quite a bit of water if the need arises to. Fog nozzles. Most fog nozzles are adjustable into a straight stream, narrow fog stream, a wide angle fog stream. A straight stream from a fog nozzle does not have a solid core of water as a solid stream nozzle or a smooth bore. You have that little round disc in the center, so it doesn't have a solid stream of water. That's why you have a better reach and penetration with a solid bore than you do the fog nozzle. Characteristics of a fog nozzle. Obviously the discharge pattern can be adjusted into your straight stream or under a wide fog. It can be used to protect firefighters with a wide fog pattern. It can be used in a variety of applications, offer a variety of nozzle choices, and can be used to apply certain types of foam. You can use these with your Class B foam when you don't have a compressed air system on your apparatus. Basic fog nozzle, adjustable fog pattern with a rated discharge at a designated pressure and nozzle setting. A constant gallonage for fog, adjustable fog pattern with a consistent discharge rate as a designated pressure. Constant pressure, which is an automatic nozzle. Adjustable fog pattern with a constant discharge rate as a designated pressure. These automatic fog nozzles allow for adjustment of the gallons being discharged by opening and closing the shutoff valve on the nozzle at different degrees. Some of these nozzles have a gallon selector on the nozzle itself. Some of these are fixed, or like it says, if you move the bail forward or back is depending on the gallons per minute you'll get out of this nozzle. Allow the operator to vary flow rate while maintaining a constant pressure. Handline automatic nozzles can reach from 10 gallons per minute to 350 gallons per minute. Constant selectable gallonage, manually adjustable nozzles allow for the adjustments of gallons being discharged by turning the selector ring on the nozzle. If you look at this one, the one here with the pistol grip in the back, you can see the numbers from flush. You can manually turn that and get whatever gallons per minute you want. On our fog nozzles, we always leave them in the 200 gallon per minute setting, especially our pre-connects. Each setting gives a constant flow as long as there's adequate nozzle pressure, so you keep the same pressure on the line. Handline nozzles may have settings from 10 to 250 depending on the size of the hose. Penetrating, piercing nozzles used to access fires in confined spaces, such as concrete walls. They work great on mobile homes. For you guys that run with rural departments, they work great on hay bales. Can pierce stucco, block, wood, and lightweight steel. Consists of a piercing tip, shaft, hose connection, and a striking plate at the end. So you can hit them with a sledgehammer or axe or whatever you have with you to drive it in. Usually driven in with a mallet, sledgehammer, or flathead axe. Cellar distribution nozzles consist of a rotating head with multiple outlets that distribute water in a circular pattern. They can be lowered into an attic, cellar, cockloft, or confined space after a hole is cut. Stream straighteners. Veins set into the water stream. It reduces the swirling action of the water stream before entering the nozzle. Most of these you'll see on your master stream devices. There's usually a short piece, could be 6, 8, 12 inches long, that has the stream shaper in it, and the same way with some solid bore nozzles will have a stream shaper in them. Nozzle control valves. This is considered a ball valve. It's the most common one we have in the fire service. Smooth waterway through it. spins from both sides of the body, nozzle body, and seals against the seat. The ball is rotated 90 degrees by moving a valve handle or the nozzle bail. When the bail is pulled backwards, the nozzle is open. When pushed forward, the nozzle is closed. When open, the waterway through the ball is in line with the nozzle water, allowing water to flow through it. You can see in the demonstration there. If partially open, the ball will create disturbance in the water stream and may affect the desired pattern. So it's either you open it all the way or you close it. If you only open it halfway, you're really not going to get the reach or the water, the GPMs that you're wanting out of that. As you can see there. Alright, the slide valves, control valve seat, a movable cylinder against a shaped cone to turn off water flow. Changing the sliding cylinder relative to the cone either increases or decreases flow, water flow through the nozzle without turbulence. Task Force Tips is the most common brand that uses this technology in their nozzles. The rotary control valve, found only on rotary control fog nozzles, basically like your little brass garden hose. A lot of these are found on booster lines. Nozzle handling precautions. Keep nozzle closed during makeup or movement of the line. So if you're moving a line somewhere around, make sure you keep that nozzle closed. Do not drop or drag nozzles. Release trapped air from hose lines before moving into a fire area. So if you get ready to go in your front yard or on the front porch, turn it to the side, open it up, make sure all the air is out of it before you get ready to go in. Operate all nozzles slowly to prevent water hammer. Move forward of nozzle if controls of the line is lost if possible. In confined areas, improper use of nozzle may upset the thermal balance and bring the heat and the superheated gases down to your level. Firefighters should be positioned on the same side of the hose line. Before opening the nozzle back up, personnel should communicate that they are ready. Make sure the guy that's backing you up ready. The nozzle is opened slowly and fully. Lean forward with legs apart, 1 foot forward, and weight equally distributed on both feet. Personnel must maintain control of the nozzle and hose line at all times. Inspection of nozzles. You want to check for external damage of the nozzle. Look for internal damage and debris. Check the nozzle bail or handle for function by moving it to the open and closed position. Check the gallonage setting control by moving it to all the various gallonage settings. Check the pattern adjustment by functioning by rotating it. Check nozzle coupling gaskets for defects, age, and ability to return to normal shape by pinching gasket between the thumb and index finger. Clean nozzle after use with soap and water and a soft brush. As always, follow the manufacturer's recommendation when lubrication of any of the parts in the nozzle. Store nozzle with the control bail closed. This keeps dirt and road grime anything else from getting up inside the nozzle and causing a malfunction. If you do have a selectable gallonage nozzle, you can turn it to the flush position and try to get any debris or anything that may be clogging the nozzle if that happens to you. Firefighting foam and foam streams. Water will have limited effects in flammable liquids fires. Proper application of foam requires understanding the various types of foam and their application. To be effective, foam concentrates must be matched to the fuel to which they are applied. Firefighting foam forms a blanket of foam on the surface of burning fuels which excludes oxygen and stops the burning process. The water in foam is slowly released and has a cooling effect on the fuel. With ignitable liquids, a foam blanket also reduces the release of flammable vapors from the liquid, preventing reignition of the fuel. The extinguishing characteristics of foam: the smothering prevents air from reaching the fuel and prevents the release of vapors. The separating creates a barrier between the fuel and the fire. It lowers the temperature of the fuel, and it lowers the surface tension of water and allows it to penetrate into deep-seated fires. Foam extinguishing agents formed by mixing water with foam concentrate and air is introduced into the foam solution. The foam concentrate is the raw liquid foam before the introduction of water or air. So as you can see here, if it's in the buckets, it is a foam concentrate. It is not a finished product. Finished foam completed product after air is introduced into the foam solution. A foam proportioner introduces foam concentrate into the water stream. Foam must be proportioned with water and aerated with air. These elements must be in correct rations to produce foam. Aeration should produce an adequate amount of foam bubbles, or the foam blanket as it's called. Foam solution: mixture of foam concentrate and water before air is introduced. For completed foam, your finished foam is the completed product after air is introduced into the foam solution. So you have the foam concentrate, which is just the foam itself, and then the foam concentrate is the water and foam mixture, and then the finished product is the foam when the air is introduced. That makes your foam blanket. That's where you get the bubbles from, is from your air. Foam expansion refers to an increase in volume when a foam solution is aerated and depends on the type of concentrate used, accurate proportioning, mixing of the solution, the quality of foam concentration, and the aspiration method. Basic foam classifications: low expansion foam has an air solution ratio of up to 20 parts finished foam for every part of foam solution. So it's a 20-to-1 ratio. Minimum expansion foam has an air solution ratio of 20 to 1 to 200 to 1. Parts finish foam for every solution through the hydraulically operated nozzle style delivering vices. Used to suppress hazardous materials vapors used in ratios of 30 to 1 and 55 to 1. High expansion foam, the rate is from 200 to 1 to 1000 to 1. Typically used to suppress confined space fires such as basements and aircraft hangars. I do believe this picture here was taken from Chicago, and that's their high foam expansion unit. And this was actually used on a liquor store fire where they stored all of their liquor in the basement, and they had a fire in the basement, and they just filled it full of foam. Types of foam concentrates. Foam concentrates must match the fuel to which they are applied. Class A foams are not designed for Class B fires. Class B foams designed for hydrocarbon fires will not extinguish polar solvent fires. The fuel involved must be identified before applying a foam. So your CAF systems on your trucks, they're Class A foam used to be on Class A fires such as room and contents fires, vehicle fires, and then your Class B foam systems are for your, as it says, hydrocarbons, gasoline, diesel fuels, kerosene, anything that's made with a hydrocarbon. Class A foams. A wetting agent, hydrocarbon, is added to reduce the surface tension of water, allowing it to soak into combustible materials. The characteristics: can be used with ordinary nozzles, can be pre-mixed in booster tank, good penetration capabilities, can be propelled with compressed air foam systems, has solvent characteristics, and mildly corrosive. Equipment should be thoroughly flushed after the use. That's with anytime you use foam, you want to make sure that you get all that stuff out of your pump and hand lines and nozzles. Class B, designed for use on unignited or ignited Class B flammables or combustible liquids. Hydrocarbon fuels float on water, and foam will float on top of these fuels. Gasoline, crude oil fuel, jet fuel, kerosene, benzene are just some of the fuels you can use your Class B. Polar solvents mixed with water. Firefighting foam must be alcohol resistant to be effective on these liquids. This is your alcohol, acetane, lacquer thinner, acids, ether. The rate of application depends on the type of foam generate being used, whether or not the fuel is on fire, whether a hydrocarbon or polar solvent is involved, if the fuel is spilled or contained in a tank, if the foam is applied by a fixed system or portable equipment. Unignited spills require less application than burning spills. Heat and thermal draft do not attack the finished foam. A foam blanket 4-inch thick should be applied to the fuel surface. If ignition occurs, foam should be flowed until extinguishment is complete. Stopping and starting can allow the fire to consume the foam blanket in place. So once you start, and if it's on fire, just keep flowing until your foam is, or your fire's knocked down or completely out. A protein foam chemically breaks down protein solids, resulting in a protein liquid concentrate. It's low expansion, excellent water retention capabilities, high heat resistance, and reignition resistance. Requires a close approach by firefighters. Protein and synthetic based foams. Long-term vapor suppression, excellent heat resistant, fast fire knockdown. Most everything that we use, unless you have a specific thing in your district or your response area, is most of the fire service uses AFFF for your Class B, and your Class A fires for your CAF system. Film forming fallopian foam is a protein base with added suffocants to reduce burn back. Develops a continuous floating film on hydrocarbon fuels. Excellent heat resistance. And it's got a fast fire knockdown. Alcohol resistant foam can be used on polar solvents at 6% and hydrocarbons at 3%. Non-toxic and biodegradable after dilution. Aquarius film forming foam, which is AFFF, which is what most departments carry, is synthetic based. It can be used to regular fog nozzles. Spreads a fast healing continuous floating film over fuels. Has a fast fire knockdown. Can be affected by freezing and thawing. May be applied directly on fuel surface. Must cover the entire fuel surface. And may be used with subsurface injection. Foam blanket continues to drain water, releasing from more film, allowing AFFF to heal over area where the blanket has been distributed. Then the alcohol resistant AFFF can be used on both polar solvents and hydrocarbon fuels. It forms a membrane on polar solvents to prevent foam blanket destruction once you have it laid down. It's got a fast flame knockdown and good burn back resistance. High expansion foam, lower water content foam, minimizes water damage and runoff. High air to solution ratio, 200 to 1 to 1000 to 1. It's got a poor heat resistance. Will attack the surface of galvanized steel and raw steel with prolonged exposure. Outdoor use is not recommended. Can be used on Class A and some Class B fires. To flood confined spaces, to reduce vaporization from liquefied natural gas spills. Foam concentrate must be proportioned with water at the percentage at which they are designed. Most of them, if you look at their buckets that the foam comes in, it will be it'll say on there what percentage to use. The percentage rates vary with the intended fuel and is marked on every foam container. Most firefighting foams are designed to be mixed at 3% to 6% concentrate in water. 3% foam concentrate is to be mixed 97 parts water and 3 parts concentrate, and 6% foam is to be mixed with 94 parts of water and 6 parts of concentrate. Class A foams are proportioned for their specific objective. A higher percentage concentrate can be used to reduce the thick foam for exposure protection and fire breaks. A lower percentage mixture can produce a thin foam that sinks into fuel surfaces. So depending on what your assignment is to do. Some multi-purpose Class B foams are designed for hydrocarbon and polar solvent fires at different concentrations. 3% for hydrocarbons, 6% for polar solvents. Portioning equipment may be designed for mobile use and others for fixed fire protection systems. The selection of proportion depends on the foam solution flow requirements, available water pressure, the cost, intended use, truck, fixed or portable, and the agent to be used. Use the pressure energy in the water stream to induct draft from concentrate into the foam stream, which is an induction or the inducting system. The Venturi principle is used in the inductors. As water as a high pressure passes over a reduced opening, it creates a low pressure into the outlet side of the inductor, and it brings the foam up out of your bucket. As you can see there, it makes your foam solution, mixes it there. Injection. An external pump or head pressure is used to force foam concentrate into a fire stream, commonly used in apparatus mounted or fixed systems. If you have a Class B or fixed foam proportioner, these will be somewhere on your truck. A concentrate is mixed with water in the apparatus water tank or portable water tanks. You can, if you have a drop tank, you can pour your foam bucket in there and mix it as it goes through your pump. It's commonly used with Class A foams. Should be used as a last resort with Class B foams. Not effective in large business because when a tank is empty, foam lines that must be shut down, and then their foam starts to break down the line. Requires thorough mixing before use. Then all components must be flushed with plain water after use, and the pump may need additional maintenance to make sure you get all the foam out of there. So don't damage any of your stuff. Pre-mixing, water and concentrate are pre-mixed in a container, such as some fire extinguishers use this. Vehicle mounted tank systems, limited to one-time application because the tank can be emptied and then you don't have anything else to mix with it. Foam proportioners may be portable, apparatus mounted, or compressed air foam systems. They operate by either the Venturi action, which induces foam concentrate into the water stream, or pressurized proportioning device that injects concentrate into the water stream at a specified ratio and higher pressure. Inline foam inductors, most commonly used in the fire service, may be connected to the pumps or along the hose lay. Manufacturer's instructions should be followed about inlet pressure and the maximum hose lay between the inductor and the nozzle. Operated on the Venturi principle. Foam concentrate inlet to the inductor must not be no more than 6 feet above the surface of the liquid foam concentrate. If the inductor is too far above the concentrate, the foam will be very lean and not be able to induct it into the your foam, your hand line. operate like any inline inductor, but the inductor is built into the nozzle, your foam nozzle inductors. It can create problems because concentrate containers must be at the nozzle and can create difficulty in relocating the line if you got to move it. Apparatus mounted proportioners. There's around the pump proportioners, balance pressure proportioners. Compressed air foam systems. The direct inject foam proportioner mixes from the foam with water on the discharge side of the pump, and then compressor adds air to the mix before it is discharged out your nozzles. The advantages of a CAF system is the stream reach is much longer than other foam system. Hose line weight less than those full of water or foam solution. Foam produced is very durable. Foam adheres well to vertical surfaces, so using for protection or exposure protection, you can use it. Your disadvantages: expense, adds an expense to cost of maintenance of the apparatus. Hose reaction may be significant. Additional training for personnel is needed. Foam delivery devices, solid bore nozzles, limited to certain types of Class A foam application, most often used with compressed air foam systems. Because your finished product is already made when it comes out of the pump, so you can use your solid bores nozzles for delivering your Class A system. Fog nozzles can be used to produce low expansion, short lasting foam. Best used with AFFF and Class A. Class A foams should not be used for polar solvents fires because of inadequate aspiration, which you're not getting enough air into your foam to create the bubbles and the blanket that you're going to need. Air aspirating foam nozzles, most effective for generating of low expansion foam. Introduces air into the foam solution through a Venturi principle. Much less reach than standard fog nozzles. Provides maximum expansion of the foam. Some manufacturers have aeration attachments for fog nozzles. Medium and high expansion foam devices. Water aspirating nozzles. Back of the nozzle is open to the airflow. Foam solution passes through the nozzle and a mist that mixes with the air. The end of the nozzle has a screen or set of screens to break up the foam and further mix it with the air. High expansion generators. Air is forced through the foam spray by a powered fan. It produces foam with higher air content, typically used in total flooding applications. Cause of poor foam generation: the inductor and nozzle flow ratings don't match. Improper cleaning of proportioning equipment. Air leaks at fittings. Too long a hose lay on the discharge side of the inductor, creating excessive back pressure. The nozzle too far above inductor, causing excessive elevation pressure. Mixing different types of foam together, resulting in a mixture too viscous to pass through the inductor. Partially closed nozzles, resulting in high nozzle pressure. Assembling a foam fire stream system. Select the proper foam to be used. Check the inductor and nozzle to make sure they are compatible. Ensure the foam concentrate matches the inductor percentage rating. Attach the inductor to hose for proper size. Attach the attack hose line and nozzle to the discharge of the inductor. Avoid kinks in the hose. Open the foam bucket and place inductor suction hose into the foam and open the nozzle fully. Increase the water supply pressure to meet the inductor's requirements. We're into the foam application methods. This is the roll-on method. Foam stream is directed at the front edge of the burning liquid and allowed to roll across the fuel surface. This method can be used only on a pool of fuel on open ground. The bank down method. Foam range is directed against an object near the fuel, such as a wall or tank shell, and allowed to run down the object and onto the liquid. The method can be used with fires and spills within diked areas or around the vehicles. Rain down method. The foam stream is directed into an area over the fuel and the foam floats down on the liquid surface. Primary method for above ground fuel storage. On small fires, the nozzle is swept back and forth to cover the fuel's entire surface. On large fires, the stream can be directed at one point to allow the foam to collect there and float out across the fuel surface. The foam hazards. Foam, either in concentrate or diluted, poses little health hazards. Can be mildly irritant to the skin and eyes. The affected area should be flushed with water, and some can be harmful if ingested or inhaled, so don't be trying to eat the stuff. Most foam concentrates are mildly corrosive. All foam equipment must be thoroughly flushed after each use. The primary environmental impact is after foam has been applied to a fire or liquid spill. When foam decomposes, oxygen is consumed by bacteria action. This reduction in oxygen in a waterway may kill fish and other aquatic creatures. The chemical properties of Class B foam vary depending on the concentration and manufacturer. Protein-based foams are typically safer for the environment. Firefighters must be adequately trained and proficient in the use of various types of fire streams available. Personnel must understand the limitations of water as an agent. Firefighters need to be familiar with the use of the various nozzles within their department and the advantages and limitations of each. Improperly used fire streams can cause injuries, damage equipment, and create additional fire control problems. Fire personnel must also understand the advantages of various types of foam and how to apply foam for the most effective result. And that is all for the fire streams until we do the practical session. So, thanks for listening.